lab 3 in operating systems. This time we'll do it really good. Okay, so what are we talking about? The agenda for today. More work with the operating system of Linux, zombie processes versus threads. Identify the PCB and memory areas. Working with threads in Linux, compiling. I don't know if we're going to actually do the compiling. Let's see. Okay. Reminder: in the previous lesson, we started getting in to know the use of the Linux operating system. We got to know some of the shell programs. We ran multiple processes using fork and use server linap. Today, we will try to deepen our acquaintance with the shell, multiple processes, threads using compiler. Why is multitasking necessary? In the previous lesson, we saw that Linux allows multitasking through multiple processes. There are situations where using multi-process provides better performance than a single process. The rest of today's lesson will be seeing that multitasking can also be done by multiple threads instead of multiple processes. For example, here are cases where we could use multiple processes. Using a web server that executes each request in a separate process. In other words, everybody's connected to the same web server. Each one's getting a specific process to handle his downloads and uploads. Dividing a large task into several parallel processes, for example, some kind of matrix multiplication, where each part is independent, you can do them simultaneously if you have, and that'll go faster if you have multiple processors and you use them by using multitasking or multi-programming or multi-processing. Interactive GUI programs that can be divided into processes, each of which is responsible for different tasks. For example, one process could be doing debugging, one monitoring user input, running the program, one monitoring performance, and all of them are running at the same time. Okay. We talked in the lecture about the PCB. It's this little box here on the left, which contains the state of the process, the number of the process, the program which is essentially a register. All the other registers, the memory limits, where the memory starts and stops in the memory. In other words, this particular program is allocated some of the memory of the computer. We need to know where it begins and where it ends. And a list of open files, which is all the files that this process has opened. This block, this actual information has to be in memory, actually all the time. Notice, even though the registers actually might change, we're going to keep a place in memory for storing the registers. In fact, I would say that we're not going to update it constantly. Probably only when we switch from one process to another will we update it, because this is really just a copy of the values in the registers. This registers thing. We don't need to change that. I mean, if we change that in memory all the time, it'll slow down our program, because we'll all the time have to write to memory. Writing to memory is a slow process, slower than writing to register. So we're not going to update this register all the time, but it's in memory in a general sense. This block contains necessary data for the running process. What do you think? Which of the following data is stored in the PCB? The base pointer, is that stored in the PCB? What is the base pointer? It's a pointer to the beginning of the location in memory from which the process was loaded. Is that in the PCB? Well, we go back. Memory limits. That's a memory limit. So yes. The base pointer is the beginning of the memory. So yes. The number of processes. That's not stored in the PCB, because it's how many processes in the whole system. And the PCB is particular to each process. Program counter. Well, that's where the program, where this process is in the lines of code. So that's specific. So yes. CPU registers, the value of the processor's registers. Well, yeah, that's going to be stored in the PCB. So actually, everything in bold here is stored. Of course, this data is not stored in the PCB of a specific process, because it relates to how many processes. This one. Okay. Which of the lists contains only information stored in the PCB? This list does not have to be complete. So which one of these things only has things that are actually in the PCB? So the location of the next command. Yeah. The contents of the processor registers. Yeah, the limits of the memory allocated to the process. Yes, so this one for sure. And the other ones? Well, no. Information about the priority of the process. That could be. Information about the memory allocated to the process. The list of all open files for sure. So that one's notable. Here, the number of processes in the system, also not. Okay, so this one's no good, this one's no good, it's only this one. Good. While running this program, we will try to see the information that the operating system holds in the PCB of the process, which is in memory. In this program, the executing process opens 3 different files, which are empty, and we use the get char command just so that we can stop the running of the program. Because every time we do get char, the program will wait for a character to be typed in at the keyboard, and that's our way of conveniently slowing down the program as we want. So the first thing, what does this program do? Well, we make our int, we make our main, we make an array, we make an array of file descriptors. FD stands for file descriptor, which means a numerical value that we use to reference the file. And the number is going to be 3. So we're going to open, we're going to refer to 3 files, and we print out this printout, which says basically, well, we're going to get argv of 0, which is the first parameter, which is the name of the program. So we're going to have the name of the program printed here, and then we're going to say PID, and then we're going to run the command get PID. So we're going to print our PID number. Fine. Then, but we only have one. We have no forking here. We're just talking about general PCB ideas without relating to creating multiple processes. Because I don't see any forks here. I don't see any threads. So we created one process. We get a PID of it. Then we go to a loop and we say, well, this sprintf, what it does is it creates a string in this array, in this buffer file name. File name is a buffer of 15 characters. So in there, we're going to put the string, which is written here, PCB demo and a number. And that number will be 0. So it'll be PCB demo 0. And then the next time will be PCB demo 1. And then PCB demo 2, and then it'll end. So that'll be the string value that we're printing to this buffer called file name. Then we're going to open a file called file name. So we're going to create, essentially, because that file doesn't exist yet, we're going to create a file called PCB demo 0, and then PCB, etc. And we're going to give it the permission 600, which is read and write for the owner and nobody else. The zeros means nobody else can read and write it. And then we're going to print out open 0 plus 1, open 1. So it's going to be 1 opened. And then we're going to wait. And then we're going to say 3 files open, because, well, that's after the whole loop, because we're going to wait, and then the loop goes again, and the loop goes again. So we're going to open 3 files, and then we're going to print 3 files open, and then we're going to close the 3 files in the loop, and say we close 1, we close 2, we close 3, and that's it. So we're just opening and closing files. All right, I explained all this. That this 600 means read write, because there is the 3 read write permissions are indicated by 3 bits, where the value of each bit can either be 0 or 1, which is either no permission is 0 and 1 is on, so that's like there is permission. So the result of is a binary number between 0 and 7, because 3 digits is read write execute. So this 3 read write execute is 3 digits, R and W and X, each digit. Either if they're all 1, then it'll be 4 plus 2 plus 1 is 7. If it would be just the first one, it'd be 4. If it would be just the second one, it'd be 2. And just the last one would be 1. And if it would be the last 2, it would be 1 and 2 is 3. So by saying 6, we're saying read write. So by putting this number here, 0, the 6 here indicates that the owner of the file can do read and write, and everybody else can't. The last 3 digits relates to different permissions of groups, because the first one is the owner of the file, which is called the user. The last one is the group, and the third one is the rest of the world, the public, which is called the other. So if we have 600, only the owner is authorized to read and write to the file. Okay, I explained that. So now let's continue. So we have this is just a review of some of the commands that we're going to, because we're going to use these commands in the continuation. So ls lists all the files that we have. The -L flag gives us an extended list, a long list. I can also just write ls. I can also write ls -L and then a file name all on one line. Even though it's here on 2 lines, it's really meant to be on 1 line. And then that means I'll list just about that file. And then there's a command PS minus EF, which displays the active processes for the current user. And then there's LSOF, displays the open files for the process. List OF, open files for process number PID. And then I gotta write a number there. Whenever you see these back arrows, this forward arrow, it means like there you're supposed to put a number or a variable. So entry, so Pico is just to open a file. It's an editor, it's like Notepad. And cat is not actually to edit the file, it's just to print the file. It just throws all the value, all the content of the file to the screen, so you can see it, but you can't edit it. Yeah, question?
Should Pico and Nano?
No, Pico and Nano is safe. So this is review, but LS, this is one interesting one. LS list open files of process. If you know the process number, you can get the process number by typing PS minus EF, because it'll give you all the process numbers. So let's see a run of this command. We will run and execute some shell commands. The program prints the process number 698 in this case, because look, here what we did. We ran the program, you see over here, PCB demo. And then it printed immediately. PCB demo is PID 698. It printed it itself. And then it says one file is open, and then we did Control Z. We suspended it, but it's still there. So now we see that if we do ls on this directory called process, or PROC, pros or proc, this directory contains in it what looks like files and folders. And we see that there is a folder called 698. And that's us, that's our process. That's a folder which is going to be all kinds of information about our process, including the PCB. It contains the directory for each currently running process. So these are all currently running processes. 65 is a currently running process, 699 is a currently running process, and then there's some other files in here. The terminal is, in this case, is 699. The terminal is also running. No, 67, sorry, is the terminal. 699 is the command to display the folders.
Where does this 699?
699 here. On the bottom left. The very bottom left. 699. That's just there's no way you could know what 699 is, but he's telling you that if you believe him, that's the command itself that we ran ls proc. And 67 is the terminal. He's just telling us that. No way of knowing. And notice there's a 1 there, that's the parent process folders. Process, and there's the parent of everybody. Process that actually, oh, I should have fixed that, something, whatever. This is a process that we actually ran. Okay, so now we can do is, now we want to make sure that that was right. We just said 698 is us, but let's make sure that that was right. So let's do PS minus EF. PS minus EF prints us all of the processes that are running, and we see that the bottom 3 are ours. And we see that the second from the bottom, 698, is ours. We're oddly apparently. And it's called PC. No, the way we ran it was by typing /PCB demo. So that's like what we call the argv. That's the first parameter of the running of the program. There's no other parameters, but that's like the name of the program that we ran. So that's the name of the process. Notice that the process PS is 67. Sorry, it's 700 now. Oh, because that's this PS. So when we ran this PS, it was running. So it had to report about itself. And so it says my ID is 700. Notice that they're both 67. Why are they both 67? Because 67 is the bash shell, is the shell that I ran. So in the parent of the process that I ran is the shell. Because I ran it in the shell. First I ran the shell, and then the shell ran this process for me. So that's why it says 67 is the PP ID, parent process. But 700 is PS minus EF, is that command. Notice that it prints me not just the name of the program, but all the parameters that I gave it. In this case, just minus EF. When I ran PCB demo, I didn't give it any parameters, so it didn't write it. But if I had, it would have written. And there's other fields here. The total time running is time. This is the command, okay. This is the term, TTY stands for the terminal. It actually is a shortened version of teletype. S time is the time to start executing the process. No, it's, I think the time when you started executing the process. Okay, let's continue. Well, these are the three user processes: the terminal, our process, then the commit. These are not our processes. These are the operating system process. They're related to the init process. The init process needed them or started them. You can see that the terminal was activated from the operating system. And he who activated the other two user actions. In other words, the process of the parent of 45, of 65 and 4 is one, which is the kernel. What did you say? You can see that the terminal was activated from the operating system is one. Why is that the terminal? That's not the terminal. The terminal is the parent of the terminal is 66, and 65 created it. See, a little bit of a chain reaction. 1 created 65, and 65 created 66, and 66 created 67, and that's our terminal. And they're all in it. Exactly why, I don't know, but apparently init calls another part, it makes a fork and another fork and another fork. It's making forks, so it's all the same process. When you make a fork, right, you're the same process name, but a different number. So it's forking itself. Okay. Oh, what do we see here? Currently, no process is consuming CPU time because all processes are currently suspended from activity. Nobody is actually active. That's why it's the C is percentage of CPUs currently used, nothing. Okay. And now this, it's a pity you can't see it really, but I believe what he did here, yeah, he did. He ran the command ls-l on us, on 698. Remember, 698 is our process. So we ran that on this directory and we got this printout. And this printout is all the information that is relevant to our process. Look how much information you have on our process. Here's the structure that represents the process, including the PCB in RAM. Now it's in RAM, it's a very important point. The Linux proc file system is a virtual file system that exists in RAM. It is not stored on the hard drive. It's not real files. A real file is in the hard drive. These are files that exist in memory. It's like I created a virtual file. So if I turn the computer off, they're all gone. It also makes it easier for the operating system to clean it up. When my process finishes, it doesn't have to delete all kinds of stuff from the disk. It just deletes all that memory. It just doesn't even delete the memory. It just says that memory, it marks that memory as not used. And it's just 1 second. It doesn't have to delete anything. It doesn't have to unmark all the different files. So these files, they look like files, they smell like files, they're not files. They're as if they're files. In the sense that I can list them, I can look at them, but they're all in memory, not on disk. That means that it exists only when the computer is turned on. You can see which files and memory areas are used and what their permissions are. Right, so you see all these different files. So that was the output of the command ls-l on the 698, on the proc/698, which is the information for our process. And now if we do cat of the file, the zip file status, we see all kinds of information. We will receive data about the running environment since the process is currently running. Most of the data is currently unclear to us and not useful to us. We don't exactly know what some of this information is. But you can search for information in this, you could probably search for something that you want. And we'll explain some of them. Here you see that's pretty clear. That's the PID of me and my parent. Here you see the data on memory areas. It's VM stands for virtual memory. How big it is. Here you see how many threads. Why is it just one? Because I didn't run any forks, I didn't create any threads, it's just one process. Okay, let's look at the maps of the file. So there's a file called maps. Here we can see the memory areas of the process in virtual addresses, of course. What do we mean by virtual addresses? Well, let's see if he explains. Here's 0. See, the program is at location 0. This is our process code. And how do we know it's our process? It can be run. Why does it say it can be run? Well, the next one can be run. Maybe I should have been a little lower. But you see the XP here. The X means it's runnable. Here is the information area of the process and the stack area. You can read and write, but not run, of course. So you see, the heap here is read and writable. And it's also in location 0. It's interesting. I guess our program was really in location 1,000, and then 2,000, 3,000, and 0. Fine. And then here is the stack, similar to the stack area, also a place 0. Now, what's all this memory? Area contains information from different DLLs. DLLs are dynamically linked libraries. We talked about that in the lecture. It means libraries that exist already on the machine, perhaps, by some other programs using it. And we just link to them when we need them. May differ from system to system. Here, for example, the library C, a C library, Linux 86 operating system, x86, that's the kind of computer we have, directory. So where do we see that? Yes, it says x86 64. That means it's a PC, 64-bit, and these are libraries. Library C. These are DLLs. All right, what he didn't explain is over here, what this is the way as I understand it, is the actual location in memory. Now, this is the virtual location, but my program thinks he's starting at 0, but really it's at this address. And we notice that they're all the same, because they're all the way are they all the same? This is C. This is to C, this is to D, this is to E. So they're incremented, that's these numbers. Very good. Okay, what about the files? So when I say what about the files, this was the PCB. We're finished now with the PCB. We explained not just the PCB, all kinds of information that is stored in memory by the operating system for my process. Now let's go back to the program. Remember, the program created 3 files. So here, if I do, actually, we're still in virtual memory. Just look what I do. I mean, first I do the cat command line, and we see the command line was just this PCB demo. Fine, not really that important. Then we do ls on the FD directory. We're still in the virtual file system, and we're doing the ls-l command. The -l is over here for some reason. Normally we write ls-l, and then on the FD directory, and in there we see the file descriptors that we've created. Now, 0, 1, 2, and 3 are given to us for free. They're always created. 0 is a file descriptor to get to the keyboard, and 1 and 2 are descriptors to get to the screen. And now we see 3 here. That's the one we created by creating this. File. Remember, our program created a file called PCB demo 0, PCB demo 1. Well, it didn't yet create PCB demo 1, but it did create PCB demo 0, and that's what you see here. And it got file descriptor 3. We asked to go to the command line. This way, you can see what data was entered as argv and argc. Well, you can't really see argc. Argc is the count, how many data, but you can see the command line tells me that there was that the first parameter is just PCB demo. We will ask to see all open files with their permissions. So the system gives running numbers to each open file. Now, when we say running numbers, we mean sequential numbers. 0, so it's 3, and then 4, and then 5. So if we let the program run, PCB demo, we do foreground, we let it run, it goes open 2, open 3, or 3 open, and now we freeze it by doing Control Z. And we see now all of a sudden in this directory, we do ls on FD, and we see 2 more file descriptors, 2 more numbers are pointing to our 2 new files that we created. So we're just showing you that the operating system is keeping track of how many file descriptors we've created and what files are open. Where are the files? Well, the files are obviously going to be in the folder where we ran the program, which is our home directory. So we were in Obvi on Obvi PC, and we do ls, and here they are. See, here we ran. Here's our program that was runnable. Notice that it's read, write, and execute. That's PCB demo. And here are our PCB demos 0, 1, and 2, and they're just readable, they're not executable. Now it says here. Oh, sorry. So these are our 3 files. You can see that they were created at the time the program was run, more or less, yeah. And the permissions are according to what we decided to give them, which is 600. Read permission, the read and write permission for the owner only. It seems this version of Linux didn't exactly listen to us, because notice that it says read write, but then it's not 0, 0, it's actually 400, 400. Remember, we go back when we created, if you look at the program, we wrote 600. That meant that the other 2 ones should be blank. But they're not. It's really as though we wrote 644, 6 read. I don't know why. That's I just remarked about that. I don't quite know what the explanation for that is, but it did listen to us. Okay. We will let the program run more now. And so what did we do? We stopped it, now we started again. Oh no, we listed it. Here, FG, we started again. FG is a command to bring to the foreground, FG stands for foreground, a program that was stopped. So we see that it says close number 3. And if we go back to the file, we'll see that it's gone. Wait, it closed all of them. Why did we 3 closed? And as it closed all 3, and we see that they're all gone, except for 0, 1, and 2, which are just the defaults, which are always there. Only when the P process is finished, the entire PCB is deleted and its memory are no longer accessible. Okay. A zombie process. What is a zombie process? Anyone remember whatever zombie process is?
When the father, when the child dies, but the father still.
Yeah, if a child dies, but
The parent's still waiting for the.
the father hasn't yet run the command.
Hasn't
Wait.
Finished yet. Yeah.
Exactly. The father hasn't died or run the command yet. When a child process terminates, its resources are not automatically lost. The PCB, that stuff that we saw in RAM, is deleted immediately. And this takes up space. The parent process or the init process needs to disassemble it, to delete it. How can the child process be disassembled? Well, the parent process can execute a wait command. In such a case, the intention is to wait for the end of the child, and then the parent, whenever the parent runs the wait command, parent process will free the memory of the child. This is an orderly and standard ending for a child process. Until the parent executes the wait, the child process will be a zombie. When the parent process eventually dies, if you didn't execute wait, then the init process will have to disassemble the child. Somebody has to disassemble it. So the child will wait around. If the father never did a wait and then exited, so then the init will have to disassemble it. A zombie means walking dead. It created when a process has finished, but its resources remain in memory because no one has disassembled it yet, either because the parent is still alive. Well, basically because the parent is still alive and hasn't done a wait. So here's an example of creating a zombie. With this program, we will try to see the memory process, the memory of a process in a zombie state. So in this program, the process creates a child process. Since wait is not executed here, the child process will become a zombie. So what do? Here's a fork, and the parent and the child says, "Hi, I'm a zombie." Why is he a zombie? Because the parent is waiting and then goes to get char. So the get char is going to stop the parent from doing anything, and the child will certainly in that time be able to print "I am a zombie," and then he'll skip the else and go to return 0 and end. When he goes to return 0 and ends, the parent has still not done wait for him. If there, if I had done something like the first thing I'd done in the child and the parent was wait, then he wouldn't be a zombie. He would have, if his divinity died, the parent would collect him. So here, before the run, there are only 2 processes. Now you can't really see it so well, but PS, Oh, before the run, you just see bash and PS, because that's all it's running, but the moment I run PS is running, and the shell is running. Now we run zombie, main waiting, hi, I am a zombie, that's the child, and now we do control Z. And that means the parent hasn't died yet. So we do PS and we see that our zombie program is running, here it is, that's 880. There's also 881, which is the child that we forked, that we created. And he is listed as defunct. When you see the word defunct, that means it's a zombie. It's dead, but it's still there. We still see it when we do a PS. Okay, let's analyze the process data. Our terminal process, so if we do PS minus F, we'll see our processes. And we see that the terminal is 67. That's this. And how do we know it's the terminal? Well, it says minus bash. Bash is our terminal. Notice the PS itself is also here. The PS minus F is 883. Our process was given the number 880. In other words, we're still in this state where everything is stopped. But there's two processes here, 880 and 881. So we can see them here by the PS command. We can also see them by the PS minus F command. And here they are, 880 and 881. It was created from the terminal, because its parent is 67. But the child process created 881, because you see its parent is 880. The zombie process doesn't seem to take up any memory space at all. Well, how do we see that? 0, it's all 0. The size of it is 0. But this is really not true because the data presented here does not include the PCB. The PCB is not really, it's whose memory is the PCB? The PCB is owned by the operating system. No, it's owned by the operating system. It's the operating system's internal information to keep track of processes. So it's not really owned by or related to the process. It's part of the operating system, so it wouldn't be listed here. That's the 0. This is the sub process, which is a zombie. Amount of memory blocks allocated. I think this is misaligned a little bit. Should be this size. The amount of physical memory actually occupied. To which processor is the process associated? The parent and the child are different processors. See, we have processor, the PSR is processor, and you see that one's on 10 and one's on 6. This guy's got a lot of processors on his computer. Multi-programming here classic. This is a classic example of the program. Because we have two processes running on two different processors. The process took almost no CPU time. Right, this is misleading because it rounds down here. It obviously took some time, but it's right at 0 because it was like less than a 100th of a second. The status of the process. Well, you see it says defunct. Okay, continuation. Now we will present the memory details of the process. So that's PS minus U gives us some more details. And you see here, let's see what we say. Here's our process. This is the process, the sub process, the zombie, right? The percent of the CPU that the process actually occupies at the moment, nothing, it's frozen. Percent of the memory, also nothing. Virtual memory, also nothing. Process status, Z for zombie. Here you see a list of the different statuses. T is waiting for input. Z is for zombie. S is for sleeping. Okay. Can you kill the zombie? You can see that the zombie process is taking up RAM because the folder exists. Here, we say ls proc 881, that was the child. And we notice that there is a process for it because some of them don't work, but here for command, whatever, the command, the root, these ones aren't there, but all this other stuff, there is stuff here. And therefore it's taking up memory, but it's obviously in the operating system. No. Even though he's inactive, also according to the status, look at the status. We look at the status, we see What do we see in the status? Well. I'm sure what he wants to say, but. Anyway, this file exists, let's substitute get memory. So now if we do kill minus 9, that's the normal way you kill a process. You say kill, and then you give the flag minus 9, that means really kill him. And you give the PID number 881, that should kill the process. We run that command and we do PS and we see he's not dead. If you shoot, this is like in the movies, you try to shoot a bullet into a zombie, he doesn't die, he doesn't react. Here we're saying kill minus 9, which is the most powerful type of kill, to 881, and he doesn't do anything, he doesn't die. So you can't kill him, because you can't, right? You can't kill him. You can't kill someone who's already dead. If we would do it to 880 and kill the parent, then instantly the child would die. So you could kill him by killing his parent.
You can't kill them, just.
But maybe you don't want to kill the parent.
How can you kill any process at all? Even the parent has its own parents. I think the parents is over the shell. So how come you're allowed to kill the parent without becoming a zombie?
You're saying when you kill any irregular process, it doesn't have any child.
Yeah.
Why
Why does it die?
why does it die? So you have to see what's the answer. You can answer yourself. It must be that in it, is always immediately performs a wait. In other words, when the parent is or the shell for sure performs a wait, and the init also performs a wait. If you kill the shell, in other words, the init is the init is the operating system. So he decides to let you kill it. When it comes to himself and he's the parent, then he doesn't make him into a zombie. When it's somebody else, that somebody else better be doing a wait.
Huh.
So if you kill, let's say you the shell itself, you kill the shell. So his parent is in it, so that's not a problem. And if you kill something that the shell created, so the child would become a zombie, but the shell is gonna wait for him.
Okay.
That could be the person who programmed the wait, the person who programmed the shell did a wait for the child. There is no choice. We will kill the father. Oh, so that's what I said. If you kill the father, you can kill the child. Right, there's no choice. You could also just let the father die. It'll eventually finish. So we do PS and we do kill minus 9 on 880. That's the father. And now we see instantaneously everything's gone. And it says to us killed zombie, which is the father. And we do PS minus EF, and we don't see them anymore. Sometimes it takes a few seconds from the moment the father dies to the moment the zombie son is also eliminated. This is because there is an intermediate stage where the zombie goes to be the child of init, and then init, which is the operating system, knows to disassemble it. An orderly exit from the process will also end the zombie. In other words, if instead of killing the process, we just let the process travel till its ultimate conclusion, then the child will also die. All right, processes versus threads. Processes and threads are units of execution of code in the CPU. Threads are often referred to as lightweight processes. In fact, we'll see that the term lightweight process is a specific term in the Linux world. There are quite a few differences between processes and threads. Below, we may also call them tasks. A program, as we may call a thread, a task. A program may divide its work among other processes or threads. Okay, either way. You can either divide your work between processes or between threads. Multitasking program is actually one process whose allotted time is divided between several tasks. So it's one process, and then you have several threads that run it, or it could be several processes. Well, if we're talking about multitasking, then usually we mean multi-threading. Processes are identical copies of the parent that run independently, but threads are not. Threads execute within the parent process using parent resources. For example, the parent's memory space, the parent's open files. Threads are therefore less resource intensive and they're called lightweight. Actually, let me say here that the way that most Linuxes, the way they work, is that when you create a thread. The operating system creates what's called a process. It creates a process for you, but it's called a lightweight process, a special kind of process that has fewer independent resources. So from the perspective of the kernel of Linux, there's no such thing as threads. Everything is a process. Some processes have more resources and some have fewer, but they're all ultimately processes, and that's why the kernel refers to them as lightweight processes, because they're still processes. We'll see. As you have already learned, multiple processes versus multiple threads. What's the difference? As you have already learned, on a modern computer, programs run concurrently. Multi-process programming and multi-threaded programming are special cases of the general concept of multi-programming. Right? It can be multi-process or multi-thread. So what is the difference? In multi-processing, if separate memory space for here, you see this as a memory space, the first row, separate for each task in multiprocessing. In other words, each process obviously is going to have its own memory space. In multi-threading, the memory space is common to all the threads. Therefore, transferring information between tasks is simpler. On the other hand, an error in the program of one task can damage the memory of the other. In other words, one thread can corrupt the data of another thread. And therefore, it's you have to be more careful what you're doing. Overhead. It's larger when you're multiprocessing and it's smaller when you have multi-threads. The time needed for creating a new thread or switching from one thread to another is shorter. It's easier to switch between them because they share more stuff. There's less stuff to copy in and copy out. Entire code base on the disk by multi-threading, whereas each thread is a single function. In other words, each process has the whole code base to itself. Whereas here, you're only running a function. We'll see how that's done. But in multi-threading, you just run a function. Each thread runs a separate function. Here's an important point. When you do multi-processing, you can actually run on different computers. You can run several, right? Decentralization. You can run on several systems at the same time. I could have different threads running on different computers. They're completely independent. So I could have different processes running on different computers and communicating with each other. And it would be called multiprocessing. But with threads, they have to be on the same computer. Ending a process does not automatically end another process. But in multi-threading, if the main program ends or crashes, all the threads will be canceled most likely. It depends on how you program it exactly, but could be killed, even if they haven't ended. Okay, so a thread. What about more about threads? So here you have a picture of. Well, let's read it. If a process spawns threads, the following factors are common to all. So we said this already. We're saying this over and over again. They have common code file. Most of the data areas of the program are the same. Open files are the same. Signal. If there was a signal sent from one to the process, and how it handles that signal, the function for processing a signal that's received will be identical in the thread. The current working directory is the same. The ID number of the process and the process group are obviously the same. There's only one process. There's no multiples. The thread ID will be different. There's a thing called a TID as opposed to a PID, which is a thread ID number. And that's how we differentiate threads. Register values are also different because they're running different programs. So they're running different functions. So they're gonna have to have different register values. If they have the same register values, they would confuse each other. A private stack section and a stack pointer within the stack. So they share the stack, but they have a section of it. Because remember, how they have to share the stack. Why do they have to share the stack? Because they share all the memory. It can't be that it has its own stack. I mean, it could be in a different location, but it has to have its own. It's essentially shared. Local variables and return addresses are shared. No, sorry, they're differentiated. Local variables because it's a function. So anything that's local is not shared. Anything that's global would be shared between threads. Signal response settings is how they respond to the signal could be different. Even though the functions are the same, but I don't have to necessarily use the function. Relative priority to other tasks. So I can prioritize the tasks. So here's a process control block. And here's the memory for my process. And that memory is divided into a text section, a data section, and a stack section. And a heap section. Now, here's the thread descriptor. In the heap, you may have, now why is it in the heap? This is very interesting, actually. Look, the text what's the text section? Can somebody remember what's the text section? What's the text section of the program? Well, that's in the memory of the memory. The memory is divided into different sections. What's the text section?
It's the program itself.
It's the program itself. So why is there only one here? Notice it's not in this list here. Because they share, all the threads share. So when I create a process, there's only one text. But look, all this stuff is in the heap. Why is this in the heap? Can somebody explain to me why it's in the heap and not in the stack, for example? Why are the stacks for all the different threads, each individual box here, there's like 4 boxes here underneath each other, like pages?
Yeah.
And they each have their own stack. Why are they all in the big box called heap?
Because you want to access them like randomly without order.
Because what?
You want to access them without an order.
No, better reason. What's the heap mainly created for? Why, when do we use the heap? A regular
Dynamically
program.
allocated.
What?
It's not dynamically allocated.
Oh, for dynamically allocated, exactly. Threads are always dynamically allocated, right? I'm running the program and then I create a thread in the middle of the run. So that thread gets created, he's obviously gonna use newly allocated memory, so he's gonna be in the heap. So we're gonna create for him a stack in the heap. And we're also gonna create a state, we're gonna keep state of this, any kind of a priority of him. The CPU register storage, in other words, when we switch between tasks, between threads, we have to swap in and swap out the data that was in the registers. We're going to store that also in the heap. So everything that's stored about it, and in this case, it's what's called user space, which means essentially the operating system doesn't have to know about it. It's in memory. The operating system said, you're one process, here's all your memory, do with it as you please. Now, when I create a thread, what do I do? What do I please to do? I please to divide my heap up into all these different parts. Obviously, I'm not going to do this all myself as a programmer. I'm going to use library functions that help me. And what do you think here? Which of the following data are common to all threads of the same process in which I'm now? Program counter. Is that common to all the threads? Each thread is a different,
Yeah, they're
is at a different point in the code, so no. Code segment. The code segment is the same. The program code is common to all threads. CPU registers, well, no, obviously it'll be different. Each thread has different values that it's adding and subtracting. The stack, well, each one has its own different stack. As it's progressing through, it's pushing things and pulling things from its own little stack, like we saw in the picture before. So everything in bold here are not in common. Question, processor utilization for threads many-to-many model. Oh, so now we're talking about models. We'll talk about this in the lecture also. A multi-core system is given as well as a multi-threaded program. Okay, so here's an interesting question. We have a multi-core system between many processors, and we have a multi-threaded program. The use of threads is carried out in the many-to-many operating model. In other words, what does that mean, many-to-many operating model? It means it's not one-to-one. It means that we have many threads from the perspective of the user. In other words, like over here in this picture. We have many threads over here. We have 4 threads over here. But they're all mapped to one PCB, to one process. What if the threads, each one was mapped to a different process? But let's say it was many-to-many. Many-to-many means they're not exactly, it's not one-to-one. It means that there's 4 here, there's not necessarily 4 here. There could be 4 here and only 2 here. There's many-to-many, different amounts of many, right? 4 threads are mapped to 2 kernel threads, 2 kernel processes. Now, what does that mean? That means that they might actually move from one, they might not be always associated with the same process. It's also possible. But let's say many-to-many, okay. The number of user level threads is, let's say, greater than the number of processing cores in the system. Okay, so what does this mean? We have a many-to-many model, and we have more threads than the number of processing cores. We have, let's say, 4 threads and only two cores. What will be the consequence of utilization for the processor in the following scenarios? The number of core level threads allocated to the program is less than the number of processing cores. The number of core level threads allocated to the program is equal. And the number of core level threads allocated to the program is greater than the number of processing cores, but less than the number of user level threads. Again, the number of core level threads, which means the real thread, the real processes of the operating system allocated to the program is less than the number of processing cores, the physical ones. In other words, there's only 2 cores. The machine only has 2 cores, but we allocated it 6 threads at the operating system level. The operating system knows about six processes, but it's only 2 cores. And the number of core, oh, that's one possibility. Then the next is the number of core level threads allocated to the program is equal to the number of processing cores. That means we have only 2 processes and exactly 2 threads, 2 cores in our computer, 2 cores and 2 processes. Or the third possibility is the number of core level threads allocated to the program is greater than the number of processing cores. So we have 2 processing cores. So we have 2 processing cores. We have 3 processes actually running. But that 3 is less than the number of user level threads, but there's 4 threads. You understand? So let's say there's 4 threads. There's only 3 processes actually handling those threads. And then there's only 2 cores handling those processes. We see how we have like different levels of I don't know what you call it, differentiation, but we can, from the level of from the perspective of the user, he's got 4 threads. The operating system says, well, I'm going to handle those with only 3 processes. And the core, there's only 2 cores actually on the machine. So what will be the consequence of utilization? So the answer. The first case was the number of core level threads allocated is less than the number of processing cores. He's got only 1 thread, let's say, and there's 2 cores. So when the number of threads at the core level is less than the number of actual processors, some processors will remain idle, obviously, because we have 2 cores and only 1 process. Because the scheduler only allocates kernel level threads to the processors and not user level. Now, even though I have, let's say, point is like this: I have, let's say, 10 threads, but I only have 1 process. I only have 1 kernel level process, and then I have 2 cores. So I can't, even though I have 10 threads, I can't use both of the cores because at the level of the operating system, I only have 1 process, and the scheduler is only going to give that process to one or the other processor. When the number of core level threads is exactly equal to the number of processors, then it's possible for all processors to be utilized at the same time. However, when a thread is blocked due to a memory failure, so a certain thread can't work, or while calling a system call, its processor will remain inactive, even if there are multiple threads using that processor. Right? There could be multiple threads using that processor. This is the problem of many-to-many. We didn't actually discuss this yet in the lecture. When there are more threads at the core level than processors, a blocked core thread can be replaced in favor of another thread that's when there are more threads at the core level than processors. So that means I have like 3 processes and only 2 cores. So if a blocked core thread, so if one of the processes gets blocked, I can take it out of the processor and put somebody else there, so I get better utilization. Okay. So more about threads in Linux. Here's a nice little picture of a user thread and a kernel thread. Let's see this picture again. This is called a one-to-one model because every thread that I create has its own process that is running for it. In order to use thread programming in the C language, the appropriate system libraries must be used, and the library is called pthreads.h. P stands for POSIX, which is a standard.
Mhm.
This library includes a number of system commands for use of threads. The threads that are created are one-to-one threads. That is, the operating system is aware of the multiple thread status and manages them accordingly. One-to-one, what we mean to say is like this picture, that every time I create a thread in Linux, a new process is created. It's a new process, but it's a special kind of process. It's a process that shares its memory with other processes. So technically, you could be correct in saying that in Linux, there's no such thing as threads. There's just processes. From a kernel's perspective, there's just processes. Some processes are lighter weight. That's what this lighter weight idea is. That means that it's a process, but it doesn't have its own memory. In fact, in Linux, process management and thread management are quite similar. And it is difficult for the user to know the difference between the two types. Therefore, threads are sometimes referred to as lightweight processes. Not only that, that's really a misstatement there. Something they're sometimes referred to as they are lightweight processes. They are processes. They're not really threads, because every thread has a process associated with it. So it's actually running in as a process. Let's go back to our zombie program. We would also like to see the details of the threads, the lightweight processes. Our process received the ID number 880, and the child process received 881. So if we go to PS minus FLC, we see 880 and 881. What else do we see? We see there's the child, the defunct child. This is the son, the zombie process. The first thread number is the same as the process number. So notice notice it says LWP. LWP is not just like a nomenclature that we made up theoretically. It's actually in the operating system referred to as LWP, the lightweight process. And what is the lightweight process for the child? Well, for the parent, what is it? It's 880, the same as its PID. But for the child, it's also the same.
Thank you. Have a good Shabbat.
Shabbat shalom. The number of threads the process creates is 1, and each process is 1 thread. Which scheduler manages this process? In this case, the local scheduler. I think TS stands for, well, not T stands for, but S is the scheduler. So what was the point of this? The point of this is that first of all, you see the word LWP, and you see that its lightweight process, which is its thread, is the same as its PID. Okay, fine. Well, we created fork anyway. We didn't create threads, so that's going to be obvious. What about if we create threads? I wonder if we will see pthread create function. So you have this function. How do we create a thread? Up to now, we just created processes. A thread is created by calling the pthread create routine, and it has all these different parameters. Well, here, for example, let's look at the example down here in the bottom. In this example, what we see is that the second parameter is null. That is attributes. That is just like we're going to say null means default. The pthread thread is an ID that we're going to give to the. We're going to receive when we create the thread. We're going to receive the ID by giving it a reference parameter. This reference parameter will be empty when we pass it, but when the function finishes, since it has a pointer to the actual object, it will now be able to assign a value to it. That's just to get the ID. And then we're going to pass it a function name. That's count. Count is actually a function name. That's the function that we want the thread to run when it says running. And this void kochavi, this v2 is a parameter that we want to pass to the function. Okay, so I explained that, pointer to where the PID of the thread will be returned, that's this pointer, that's this ID. Pointer to desired properties, well, we're gonna give it null, we're not gonna use the default properties. Usually attribute will be null with default properties. A pointer to the function that will be the main program of the thread, that's this count here. And then finally, a pointer to the parameter that is passed through that, that's the v2. It's hard to read that, but the one parameter is required, the pointer arg can point to a struct, right? We only can put one value here, but that value could be a struct, so there are many values inside it. Sorry, okay, so functions related to child threads. So there is two main functions other than creating them, and that is pthread exit. A normal exit will, what will a normal exit do if I run that in the thread? Since the thread is part of the main of the same process as the parent, what will exit do? Well, if the child exit, if the thread exits, the exit the exit command is a process level command here. So it'll affect everything in the process. That means it'll kill, that means even though the child thread exits, it'll kill the parent. A thread can end its run by calling pthread exit. If it calls pthread exit, then that just means the thread ends and not the parent, or not the process. Even if the parent process calls pthread exit, he will die, but the children will go on. The function takes a pointer parameter. This pointer is used to pass the value as a result, the terminal code to the parent task. Fine. The function pthread join. Pthread join function causes the thread, usually the parent, to stop and wait until one of his childs finishes. It's kind of like the wait command that we saw for processes, but now we call it pthread join. We call it join, not wait. The command receives the PID of the thread you want to wait for. Really, it shouldn't be the PID, it should be the TID. If there are no children, if there are no child threads, then it'll immediately finish. The pthread join won't wait, it'll just say, oh, there's nobody to wait for. It'll return the value -1 to indicate that it failed to wait for anybody because there was nobody to wait for. You can specify another parameter through which the return value of the completed thread will be returned. I think we have an example. So here, we say it like this. Here's our count program. And it does whatever it does. And here we do pthread create. And notice that ID1 is well, pthread type is just like an int. So this is an int. And then we don't give it any value, but we pass as a parameter because we're going to get a value put into it. Then null is our default attributes. Count is the name of this function. And a void star, well, the parameter has to be casted to a void star. And it's v1, which is the value 1. We pass it by reference, the 1. So that means that this function will now get run by this pthread create command. And he'll start running. And he'll get the parameter, which is the value 1. And he will copy that value. First, he'll cast that value from a void pointer to a star to an int pointer. And copy it into a local variable. And now I can take you see there was a pointer that I got, I need to dereference it, and that'll be my actual value, and I got the value 1, and I print 1. Very good. And now the child, the other one, gets v2, and he'll print 2. And then the parent will print the word parent, and it'll do sleep. Why is the sleep here? Well, the sleep here is just to sort of hope, it's not really a very good solution, but it's to hope that the children will print before the parent finishes. Because if the parent wouldn't finish, if the parent wouldn't have a sleep here, he might finish, and the minute he finishes, the children will all die. Once the parent dies, the children will all die because they're in the same process. Unlike processes. When you create a separate process, the parent dying doesn't kill the children. So now I have to compile it with a special flag, -pthread. Actually, when I do it, I usually write -l pthread, but here's -pthread. And then we run it and we see child value 1, child value 2, and parent. It's interesting that the parent printed there's no way of knowing the order here. Technically, it could print in any possible order. Because the child 1, just because I ran in first, doesn't mean he actually track the CPU first, and this is the most likely order. Or actually, the parent could have been, the word parent could have been printed earlier, because it takes some time to create children. But since they're likely processes, they're created faster, and therefore it might actually print out the way it is. Okay. The only thing that's missing from this lecture is we didn't show. We didn't stop this program in the middle and then do the PS. Minus FLC, that would have been interesting to see, but what the lightweight process numbers are for the children. I think we would have seen there would be different numbers, it wouldn't be the same number as the parent, because even though they're threads, they're actually separate processes. Okay, in the remaining time, you do your homework. There's no homework here, but there is homework. The homework that you saw. We can work on that or we'll finish. Okay. Stop share.